You can come here and watch the video of that particular lesson. I have an entire recorded lesson for this particular topic, as well as here you can watch somebody else's take on it. So then tomorrow we'll discuss double bonds, triple bonds, then Thursday, resonance isomers. Then Friday, discuss molecular shapes. Yeah, all right. I think we're actually caught up with everybody now. So that's good. We lost some of the other classes were a little bit ahead of us in like 2 weeks ago, but I think we're actually good now. All right, so let's take a look at this without further ado. As always, it's okay. As always, when we look at this, we have the unit name, and then you can see we've got a lot of state standards here. So a lot of state standards. Here are your standards-based objectives. You should be able to checklist these. Like, I know the difference between this. I can do this. I can do that. I can do this. So the first thing we have is a quick review from last semester. Molecular versus ionic bonding. So last unit, we taught you about valence electrons. Well, you've learned it several times. If we recall, valence electrons are the electrons that are furthest away from the nucleus. They're the outermost energy shell electrons. These are the electrons that interact whenever atoms come together. Some atoms lose electrons while others gain electrons to form ions. And others just share electrons to form what we call molecular bonds. So ions are atoms that have gained or lost electrons, and then you have this electrostatic force that makes them stick together, versus things like hydrogen and oxygen can do what we call sharing. So this is ionic. This is a molecular compound. Now, if you recall, we name ionic compounds by naming the metal and then changing the ending of the non-metal to IDE. So this is sodium iodide. Remember that? Sodium iodide. We name the molecular compounds by counting up the atoms and using prefixes. So this would be dihydrogen monoxide. Molecular bonding uses prefixes. Ionic bonding makes sure the charge is balanced. Ionic bonding, there is a transfer of electrons from one thing to another, and then they electrostatically attract each other. Positives attract negatives. When we name that, we name the cation, the metal, magnesium, and we change the ending of the anion to IDE. Magnesium chloride would be magnesium mixed with chlorine. The problem here is that magnesium has a 2+ charge and chlorine has a -1 charge. So what is the true formula for magnesium chloride? It's not just MgCl. What do we need? Anyone? What is the formula for magnesium chloride? Give you a second to think about it. I'll only make 2 and 1 capsule. Yeah. Oh, look, we got some chats. In the chats. Oh, you check the cannabis. Yeah, just see me right after class. Anybody? How do we make this magnesium and chlorine cancel out so that they don't have charges? If you were with me last time, you would sit there and say, okay, which currently is the least number, 2 or 1? 2 or 1? It's a question that anybody should be able to answer. What is smaller, 2 or 1? 1, right? So we make another one of these ones. So now we have 2 positives and we have 1 plus 2 negatives. Are either of these smaller, 2 or 2? Or do they cancel out? 2 cancels 2 out, so we have 2 positives and 2 negatives. So the formula for magnesium chloride requires 2 of these chlorides. The other way you could have done it is the least common multiple of 2 and 1 is 2. 2 divided by 2 is 1 magnesium. 2 divided by 1 is 2 chlorides. Either way. Now, ionic bonding, again, is these electrostatic forces. The characteristics with ionic compounds, they are solid. This is sodium chloride. Nice chunk of salt or halide, as it's called. Consists of a metal cation and non-metal anion. It is electrically neutral. It is crystalline, as you can see at room temperature. To melt this would be difficult. We would have to reach a high temperature. It is named by the metal sodium that's mixed with the chlorine. We change the ending to chlorine to chloride. The simplest amount of this I can have is known as a formula unit. So the simplest amount of water I can have is known as a molecule. The simplest amount of an ionic compound I can have is known as a formula unit. Now, as composed to ionic bonding, we have molecular bonding. Now, molecular bonding compounds basically fulfill the octet rule, which is a set of 8 by sharing electrons instead of transferring electrons. So they don't gain or lose electrons, they just share. The elements involved in the molecular bonding are not metals. So if we see a metal, we know it's ionic bonding. If we don't see a metal, we know it's not ionic bonding, it's molecular bonding. We can characterize molecular compounds as having not metals. They are electrically neutral by sharing electrons. They can be any state of matter at room temperature: liquid, H2O, gas, carbon dioxide, solid, silicon oxide, which is silicon dioxide, which is sand, or carbon monoxide, which is a gas that you breathe out. So they can be any type of matter: solid here, liquid, and gas. They typically have a low melting point, and they're named by using prefixes: dihydrogen monoxide, carbon dioxide, silicon dioxide. The simplest unit of a molecular compound is known as a molecule. All right. So Lewis structures and the octet rule. Basically, Lewis structures is a way to draw out what we think a molecule might look like, how the atoms are arranged and how the electrons are arranged and what shape they're in. This allows us to get a good idea of its character and how it might react. So the first step of drawing these out is to count up the valence electrons. Many ways to do this. One way is to have the electron configuration. Look for the highest level, 3. 2 plus 3 is 5. So P has 5 valence electrons. Easy enough, right? The other way is you can look at your periodic table. Find P on the periodic table. Oh, look at that, 5A. P has 5 valence electrons. That V is a Roman numeral 5. So P has 5 valence electrons. Let's say we have something like pH3. So we have 5 valence electrons for the P, and we have H. Well, 1s1 for H. 1s1, 1 valence electron. Each H has 1 valence electron. How many H's do I have? I have 3. So that means I have 3 valence electrons total. If we add this up, pH3 has 8 valence electrons total. Easy enough. How about CO2? Well, find C, 4. Find O, 6. We have 2 of these in CO2. 6 times 2 is 12, plus 4 is 16. 16 valence electrons. Using the periodic table, go ahead and do exercise 1 real quick. Give me a second or two. Count up the number of valence electrons for each of those. This is one of those things that if you can't do this, you're done for the rest of the chapter, because this is a requirement to do everything we do past this day. Keep that in mind. So N has 5, H has 1. We have 3 H's. 5 plus 3 is 8. S has 6. O has 6. We have 3 that have 6. 3 times 6 is 18. Carbon has 4. We have 2 of those for a total of 8, plus 4 for the hydrogen. We have 12. PCl3. P has 5. Cl has 7 times 3, which is 21, not 27. So it's a total of 26. So that's the key to first doing this. We have to find out how many valence electrons we have total to work with. Valence electrons are the only electrons that we're going to be able to use to create bonds. The octet rule says atoms and molecules usually have 8 valence electrons around them. Hydrogen is an exception, with only having 2 electrons around it. But that makes sense, since hydrogen only has an s orbital, 1s, right? And the s orbital can only hold 2 electrons. So that's why hydrogen is an exception, because it only has the s orbital. Now, something that's in the second period would have s and p. So it would have the ability to have 2 in the s and 2 in each of its p orbitals, for a total of 6 plus 2, which equals 8. So this is why we learned all this stuff, this s and p stuff, is so that we could see that we have these 8 orbitals. I'm sorry, these 8 electrons in these orbitals. Together, these 4 orbitals hold a total of 8 electrons. Hydrogen, again, only has an s, so it only gets 2. Now, either a straight line or a pair of dots is used to represent electrons. A pair of electrons shared between 2 atoms is referred to as bond. A pair of electrons that is only on 1 atom is called a lone pair. So let's take a look real quick. Here we have P. P has 1s. P has 2s. And P has 2p. 1, 2, 3, 4, 5, 6, 7. right? Oh, I'm sorry, P has also this. Let's do this. Then we have 3s. Then we have 3p. 8, 9, 10, 11, 12, 13, 14, 15. I'm going to redraw this one because I don't like the way it looks. So this is that box diagram of our P. Right? All of these electrons don't matter because they are close to the nucleus, right? It's only this outer valence electron shell that matters. So we have 2, 3, 4, 5. A P needs an octet. So it needs to gain or somehow get 3 electrons. So if we take a look up here, we have pH3. So watch this. H, H, H. How many electrons does each H have? 1. So each H here is going to share an electron with the P in each of these orbitals. They're going to kind of bring their orbital close enough to match up so that they are now sharing these 3 bonds. So what does P look like then? Well, P looks like it has 3 bonds, 2, 4, 6 total. We're trying to get up to that octet, 2, 4, 6. Well, don't forget about these 3 right here, or these 2 right here in this 3s. That is what we call a lone pair. So now P has 1, 2, 4, 6, 8 electrons. One of the electrons making up this bond is from the P. One of the electrons making this bond up is from the H. Same thing here and same thing here. So that is the understanding behind it all. This is why we have an octet. This is why H doesn't have an octet. It only needs 2 because it only has an s orbital. This is how these 2 electrons here and these shared electrons from these orbitals all work together. Let's try some more. So let's try HF. Well, F has 7 valence electrons. H has 1. So if we do F, F has 9 electrons total. 1, 2, 3, 4, 5, 6, 7, 8, 9. So only 1 needed here. That H is going to provide that 1, and you're going to get that bonded to the F. But look here, 1, 2, 3, right? 1s, 2s, 2p, 2, 4, 6, 2, 4, 6. There are those valence electrons, and then that last orbital is being shared between H and F, so that F gets 2, 4, 6, 8. Now let me show you how we can do this easily. We don't have to do this every time to think about it if we understand why it happens. So we have nitrogen plus 3 iodine. So nitrogen triiodide. Right? Nitrogen triiodide. So we have 5 from the nitrogen and 7 times 3, which is 21 from the iodide. That's a total of 26 electrons to play with. And here's the new game. First, we want to find out what goes in the middle. We want to branch out from one middle atom. The middle is always what we call the unique one. With HF, we didn't have one that's unique. There's no true middle. With Ni3, there's only one of these nitrogens, so it's going to go in the middle. We're going to make bonds with the iodides around it. Boom. We have 3 iodides around it. We have 26 electrons to do this whole thing, right? 26 electrons to do this whole thing. Well, I just took 2, 4, 6 electrons from that 26 because each bond is 2 electrons. 2, bond to the middle. All right. 3, subtract bonding electrons. So 26 minus 6 bonding electrons gives us 20. Means we're going to have 20 electrons in the lone pair section. Well, does iodine have 8 electrons around it? It currently only has 2. So 2, 4, 6, 8. So right there is an extra 6 electrons. 2 around this iodine, 4, 6, 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So by putting an 8 or an octet around all of the iodine, I've used up 18 electrons. I have 2 more electrons, but look at nitrogen. Nitrogen has 2, 4, 6. It doesn't have 8. It needs 8. So we put the next pair of electrons on the nitrogen. Remember, we can either use dots or lines. I use lines most of the time. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. 26 electrons used up. And we had 26 electrons to use. So subtract the bond electrons. 4, give everybody that needs one an octet. Easy enough. If you have trouble with that, you can watch the video again, as I said, or if you're a better reader, then you can read down through here. These notes are a little bit quicker than that. Now here's the deal. The only thing I did not do is I did not call this, what they call it, is a skeleton structure. That's a skeleton structure. A skeleton structure has the bonds, but it doesn't have all of the lone pairs. So let us try another one. CCl4. How many electrons are there? Can anybody give me an answer on that? You can type it into the chat. I'll open up the chat for you even. How many electrons are there? CCl4. So Cassidy, how many electrons is carbon going to bring to it? Cassidy, how many electrons is carbon going to bring to it? No? Cassidy. Cassidy Bullard? Mm-hmm. Landon, how about you? Carbon. How many electrons does the carbon have? How many valence electrons does carbon have? What is this Roman numeral? You guys are having trouble? Oh, there we go. My speaker doesn't work. You mean your microphone? Can you hear me okay? 6 electrons. Unfortunately, it's not 6. Try again. It's the I before the V. So you know that V is 5. So I before V would be Amani, how about you? You guys don't know Roman numerals? Amani, do you know your Roman numerals?
I just can't see it.
Can't see it. Okay. You need to get a periodic table printed out at home. Let's try this. So here's carbon. We have IV. So what does that mean, IV?
Is it 5?
Nope. So we don't know our Roman numerals. V is 5, right? And I is 1. So if I want 2, then I would have 2 I's. If I want 3, I would have 3 I's, right? So you're thinking if I wanted 4, I might have 4 I's, but that's not true. If this is 5, then if I put 1 before the 5, that is 4. So carbon has 4 valence electrons. So we're going to take that 4 and we're added it to Cl. There are 4 Cls. We're going to take 4 times whatever we get for the Roman numeral for Cl. And what is VII? Redemption, Amani? Amani? So we know V is 5, and these 2 I's are after the 5. So what do you think?
Seven?
7 is correct. Good. You can't do any more problems in this unit if you can't read these things. So very good, 7. So keep that in mind. You won't be able to do anything else if you can't read these. So we got to get you to that point. So if it is 7, we have 4 plus 4 times 7. 4 times 7 is 28. 28 plus 4 is 32. So that's 32 valence electrons that we have to put around the structure. So then it says, draw the skeleton structure. Well, out of C and Cl4, which one is unique? The unique one goes in the center. Yeah. The Cl4, there are 4 of them, right? So that's not very unique. Unique means that there's like a one of a kind. So carbon. Carbon's going in the center. Cl is going around it. That is the skeleton structure. Right? And then it says add lone pairs to give each one 8. So we're going to draw the skeleton structure again. We're going to add lone pairs to give each one 8. Carbon currently already has 8. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So now everything has 8. We've used the 32 valence electrons. How many electrons did I use? 32. Is this the same answer as in answer A? Yes, it is. So that is the structure. That is the what we call the Lewis diagram, named after a very famous chemist with the last name Lewis. All right, so try your skill on NH3. NH3, and I will give you, here is N. You should know H already, but NH3, try your skill at drawing it out from scratch. NH3. All right. So who is in the center? I got the chat up. If your microphone doesn't work, you can put it there. If you can't tell me who is in the center, can you tell me at least the number of electrons that we have to deal with? Ka? You got the number of electrons, nitrogen, what's this? How many is nitrogen bringing to the party? What is Roman numeral V? How many is that, Ka? Dun, 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 dun. V is not 4. 5, there we go. So nitrogen is bringing 5 to the party. And how about hydrogen? My bad. Hydrogen. How much is hydrogen bringing? 1. How many hydrogens are there? 3. So we're going to add 3 to that. Gives us a total of 8. It says, remember, hydrogens bond once. Hydrogen atoms do not receive any lone pairs. Who's going in the center? NH3. Which one is unique? The nitrogen, said in class. So that means hydrogens are going around it. Hydrogens only bond one time. They don't need an octet. We have 8 available. Here is 2, 4, 6. And that nitrogen is going to get that lone pair. Boom, boom. All right. Please go to page 13. I want you for homework tonight to do problem number 1 on page 13 for tomorrow's homework. Problem number 1 on page 13 for tomorrow's homework. Have a great day. If you have questions, by all means.